Yeah? And now I'm going to add these together. Now when we add half reactions together to get a whole reaction, we need to make sure that the electrons cancel. Are they going to cancel when we add these two reactions together? Yep. Yes, they will. So when we add everything on the left, we get Cu plus 2 plus Zn0 plus 2 electrons. And on the right, I get Cu0 plus Cn plus 2 plus 2 electrons, and the electrons cancel out. So we have taken two half reactions off of the table, turned one of them around to make it oxidation, and then added them together, making sure that their electrons cancel, to make a whole reaction. What would have happened if I'd have had this instead? Then instead of using the copper half reaction, I would have used the silver half reaction. Yeah? And before I added them together, what would I want to do?
Divide by 2.
Do what? Why would I want to do that? I need to cancel out the electrons out. So when I added these two half reactions together, I get 2Ag plus Zn0 plus 2 electrons, double, gives me 2Ag0 plus Zn plus 2 plus 2 electrons, and the 2 electrons would cancel out. Another way of thinking about how we balance oxidation reduction reactions. Yeah? How we doing? Now, the other thing that we use this table for is to see whether an oxidation reduction reaction is spontaneous or to write one that is spontaneous. One that has a delta G that is negative, just to relate it to a couple of chapters ago, but one that's going to happen. In other words, if I put zinc metal into a solution that contains silver ion, is something going to happen, right? Is in fact the silver going to take electrons away from the zinc? Well, back when we first did this, here's what we thought about. We put the elements in order by who likes electrons best. We called it an activity series. Remember that? And we made sure that the element that likes electrons the best was taking electrons away from the element that didn't like electrons so much, right? Now, is that true here? Let's take a look. Where are the two half reactions in relation to one another? Silver is higher. These are in order by electron affinity. They're in order by who likes electrons best. Fluorine likes electrons the best. It's at the top. The alkali metal's there at the bottom, right? So if that's the case, then silver must like electrons better than copper. Yeah? And is silver taking electrons away from copper? So this should work, huh? Yeah? Silver likes electrons better. It's taking electrons away from copper. Zinc, excuse me. Okay. Yeah. No wonder there was a little silence there. Copper. Doing it again. Sounding like Jim Gaffigan.
What?
Jim Gaffigan is?
Oh yeah, isn't he the hot book?
My wife and my daughter's favorite comedian. They listen to him over and over and over again. They love him. I was mildly amused the first time I saw him. How we doing? So we can use this table then, like we used the activity series back in chapter 8. We can use this to, number one, be able to tell whether a reaction is spontaneous or not, who likes electrons better, who's taking electrons away from whom. And number two, we can actually use these to write spontaneous reactions. For instance, is this reaction spontaneous? Where's my list of reactions? Now, if you're looking at half reactions, you have to look at the right one. There are two half reactions on the table that involve iron. See them? The lower one is where Fe plus 2 is becoming iron metal. The higher one is where Fe plus 3 is becoming Fe plus 2. Which one would we want to be focusing on here? The higher one, huh? Because we're starting out with Fe plus 3 and it's becoming Fe plus 2. Not iron metal, right? See why we're going to focus on that one? Then we find the tin half reaction. Got a tin half reaction there?
Yeah.
It's between the two. Below the hydrogen one.
There's tin plus 4 becoming tin plus 2, then there's a tin plus 2 becoming tin metal. But both of them are below the reaction for iron that we're looking at, aren't they?
Yeah.
Okay? So the iron is going to be able to take the tin 0 to tin plus 2 and then on to tin plus 4, in other words. So this reaction is spontaneous as written. Okay? Again, we say spontaneous as written. Why do we add those words as written? Because the reaction is reversible, we've determined that it's spontaneous in the forward direction. What do we know about the backwards direction? Not spontaneous. In other words, if I wrote the reaction like this instead, just the reverse of that, this direction is not spontaneous. So an oxidation reduction reaction is going to be spontaneous in one direction or the other, isn't it? So when we say, is this reaction spontaneous, we say, as written, with the reactants on the left and the products on the right. In other words, if I mix these chemicals together, these two things together, I would get a lot of this and not much of that when equilibrium is reached. In other words, a spontaneous reaction is going to have a relatively large KEQ, isn't it? Okay? And by the way, just a little aside, the value of KEQ is directly related to the value of delta G. In fact, we can calculate KEQs from delta G, and we can calculate delta G from KEQs.
Delta G is confusing.
Again, if you're going, yeah, delta G, I'm not so sure. Don't worry about it. You won't see delta G again on test in this course. Okay? All right. Who likes electrons?